Valence bond theory, or hybridization orbital theory, which is the same thing, is a really interesting phenomenon, and I think it's best just to show an example of how this works out. So let's talk about boron trifluoride, BF3. Boron is one of the elements that can make a molecule without an octet. So that means boron here only has 3 fluorines around it. It doesn't need the 4th one. Boron, beryllium, gallium, aluminum are the ones that can be under. But anyway, boron's atomic electron configuration is a 1s2, 2s2, 2p1. Remember, boron has 5 electrons total. The electrons go in 1s first, 2s, etc., etc. So how do you go from spherical 1s and spherical 2s? And these 3 2p's, they're basically at figure 8s to each other, but they look something like this. It's really hard to draw the Z. It's like coming out of the screen at you and going into the screen. I'm not an artist, obviously. Anyway, how do you go from these 90-degree P angles and no angles with the S's? How the heck do you get that into a planar triangle or trigonal planar angle at 120 degrees? And that's the question here that valence bond has to answer. So again, this is really important. How the heck do you go from the atomic orbitals into the molecular orbitals? How do you go from things which are at best 90 degrees apart into 120? Pauling said that in valence bond, what happens is the central atom is hybridized. And hybridized just means that you're taking some of the atomic orbitals and you're mixing them together. And the new orbitals that come out are called hybrid orbitals. And it's an energetic mix, if you will, of the atomic orbitals. So these hybrid orbitals are really interesting, all right? You literally take the atomic orbitals, you mix them together, and out pops these new hybrid orbitals. And because they're all essentially at the same energy, they're going to try and be as far apart from each other as possible, and that's how we get the correct geometry. So let me show you an example of this. Boron has a 1s2, 2s2, 2p1 electron configuration. I'm not going to show the 1s2 because those are deep in the core of the atom. All right, they're not part of the valence electrons. So 1s2 doesn't interact in the bonding of boron trifluoride. So what Pauling said is you take then this 2s2, 2p1, those 3 electrons in 4 orbitals, by the way, and again the 4 orbitals, 1, 2, 3, 4. You take those 3 electrons and you hybridize them, which means you essentially mix them together to a new energy state. And for boron, in boron trifluoride, what that means is you're going to have 3 orbitals, which are these hybrid orbitals, and they're all the same energy. And in boron's case, there's going to be an unused p orbital we're going to talk about. So you can think about it, like I said then, is you're taking these 3 orbitals and you're mixing them. This one just goes straight down and is unused in this case. And if they're all the same energy, then by Hund's rule, you want to keep the electrons in their own room without pairing them up. So the paired electrons each go into 1 orbital. These new hybrid orbitals he referred to as sp2. And that comes from the fact that it's 1 part s and 2 parts p, all right? The other p orbital is unused. So each of these new orbitals with 1 electron is referred to as an sp2 hybrid orbital. And if they are the same energy, 1 electron goes to each one, and through the ideas of VSEPR, which was all about electrons getting as far away as they can from each other, 120 degrees would be the right angles, because if they're all the same energy, 1 electron each, they want to get as far apart from each other as they can. So VSEPR says, yeah, this is going to be all at 120 degrees. Here is a picture kind of as to what's happening. So in this picture, it's kind of hard to see, but the boron atom would be right in the middle, all right? And around the boron, you can see are three of these kind of mushroom-looking things. It's the best way I can describe from it. Each one of those mushrooms, like here's a mushroom right here, and there's 2 and 3 of them. Each one of those mushrooms is an sp2 orbital, and there's math ways that you can draw out those structures, which we're not going to talk about right now. In reality, the mushrooms are a lot bigger, so this is what shows it right there. But because they're all the same energy, they all have 1 electron, and electrons want to be as far apart from each other as they can. That's where the trigonal planar geometry comes from, all right? They want to be far apart. They're 120. So when you make a molecule like BF3, it naturally takes up trigonal planar 120 degrees. So again, in this hybridization valence bond theory model, the atomic orbitals are mixed or hybridized into same energy orbitals, which they refer to as degenerate. All right, degenerate here means the same energy. And those orbitals with the same energy, the electrons are spread out, and they want to be as far apart from each other as they can, i.e. valence shell electron peripulsion theory, VESPER. That's where the trigonal planar comes from. At this point, in boron, you have 3 individually filled hybrid orbitals, so 1 electron per sp2 orbital. And that's what's used to make then the planar BF sigma bonds. It's kind of an interesting idea. This picture right here is pretty cool because it shows, and we saw it earlier, it shows the atomic orbitals on the top and the new hybrid molecular orbitals, if you will, on the bottom. There is the unused orbital. We won't talk about that. Now, one more thing. When you make a BF bond in BF3, the fluorine is not hybridized. All right, this picture right here of that yellow kind of figure 8 shows that singly occupied 2p orbital we talked about earlier. Fluorine is literally just hanging out with its atomic orbitals. And to make the sigma bond, which is the interaction, you need the blue, one of the blue sp2 orbitals with a single electron, and you need the yellow 2p orbital from the fluorine. They smash together and it makes the sigma bond, which is what we draw when we draw the molecule like right there. So it's really interesting idea. The central atom in the molecule is hybridized. So we would refer to boron as sp2 hybridized. But the outside atoms, like fluorine in this case, they're just using their atomic orbitals. They are not hybridized. So it's the atomic orbitals on the outside with the hybrid orbitals on the inside. They smash together to make that sigma bond. BF3 is born. The right-hand video, which I'll show you in a second, is for BH3, which is similar to BF3, only with hydrogen you would have 1s orbitals instead of 2p. So you can see there that the hydrogens 1s and stuff, they want to get as far apart from each other as they can. They're all the same energy and stuff. The trigonal planar comes out naturally. Don't worry about that SN3. That refers to something else we haven't talked about. Pretty cool. So to summarize here what's going on, in valence bond theory, all right, you look at the central atom, and we're going to apply a term to it. For boron, it's sp2 because the hybrid orbitals on that central atom came from 1s and 2 p's. It's a little weird, but that's what that means. So we would say the boron is sp2 hybridized. We can look at other types of molecules to see other kinds of hybridization.